Okay, calculus students. Sorry I'm not with you today, but we're going to charge on, and we're still in this unit 4, exponential logarithmic functions. Today, what we're going to do is we're going to graph exponential functions. So bear with me. It's been a while since I taught virtually. So we're going to graph. That's my topic. Graph exponential functions. And let's see. The equation, the general form, I will say f of x equals b to the x, which you've seen. You've seen exponential before. You've seen them. They look like y equals 2 to the x, y equals to 1/2 to the x. We've played with exponential before. B is considered the base. So there's a B, there's a B. Now you're going to see where the author is talking about an A and a B. And it's not going to be very clear with this problem right here where the A is. So really, I just need you to look at the B. It's a 2. 2 is greater than 1. 2 is greater than 1. That means I know that this will be an exponential growth. All exponential growth problems look like this. They have a horizontal asymptote, and then as you approach to the right forever, as you approach to infinity, f of x approaches to infinity, goes up forever. That's what it means to be a growth. Well, how am I going to graph this? All I really care about is realizing that 2 to the x does not shift up or down. If y equals 2 to the x plus 0, that means it doesn't go up and it doesn't go down. That means the horizontal asymptote has to be the x-axis. I just need to get one very good point. And I will take what happens when x is 0. When x is 0, I get 2 to the 0. Anything to the 0 power is 1. So when x is 0, I have that dot here. And since 2 was bigger than 1, it's going to be a growth. I know for a fact that it's going to go up this way. I could do better and get extra points, but I don't have to. Now, as I go to the left forever and ever and ever, I will approach the horizontal asymptote. So that's my basic graph of an exponential. So when b is greater than 1, we call it exponential growth, and it's increasing as I go to the right. If b is less than 1, 1/2 is less than 1, it's going to be a decay. And also, take a look at this. F of x is 1/2 to the x plus 0 again. That means it doesn't go up or down. It never shifts up, it never shifts down. So, horizontal asymptote at the x-axis. And if I plug in x equals to 0 again to see what happens, I get 1/2 to the 0 power. And anything to the 0 power is still 1. So I also have an ordered pair at 0, 1. But it's a decay. This is a decay. Decay means that as I go to the right forever, it's getting lower and lower and lower. But to the left forever and ever and ever, it's going to go up. So that's a good generic graph. So now we're going to do some more of these, and we're going to try to describe the usual. Is it a growth? Is it a decay? What's the domain? What's the range? What's the y-intercept? That means when x equals to 0. I'm always going to do that. The asymptote will always be a horizontal asymptote. We'll describe the interval of increasing, the interval of decreasing if it has one. Remember, we're only going from left to right. And behavior will be as x approaches to infinity. What does f of x approach to? As x approaches negative infinity, what does f of x approach to? We've done this before. So the problem we're going to start with is 3 to the x. This is not any different than we just got done doing. 3 is greater than 1. Therefore, it's a growth. When x equals to 0, we know f of x equals to 1 because 3 to the 0 is 1. So over here, here's my 0, 1. It's a growth. So I know it's going to go this way. Nice, smooth curve. Now, if you really want more detail, you could talk about x being 2, and that gives you 3 squared is 9. Well, that would change my picture a little bit because at 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, I guess I should have thought about 3 being a big number. That the generic graph looks like that, but in actually, this graph's got to go a little steeper because 3 is a big number. So it becomes a vertical stretch. So go ahead and add one more point just to make it prettier. And then there is my better curve. This is what I do when I just want a fast sketch just to see, well, what does it look like? But in reality, 2 comma 9 would be another good point to use. So good students would want to make it look better. So it's a growth. The domain, if you look very carefully, as I go to the left forever, every x is being used. As I go to the right forever, even though it's steep, eventually every x will be used. It goes forever. So how do we do that? We say negative infinity to infinity. Now the range is the y values, and we know that I have a horizontal asymptote at y equals to 0, but it does go up forever. So what I'm going to say is it cannot equal 0, but it can go up to infinity, but it can't be equal to infinity either. And the y-intercept would be 0, comma 1. And the asymptote is y equals to 0. This function does increase on its entire domain, so it increases from negative infinity to infinity, from left to right. It never decreases. As x goes to infinity, f of x goes up to infinity. As x goes left forever, negative infinity, f of x approaches 0, because that's the horizontal asymptote. As x approaches negative infinity, the y value approaches 0. Let's do a decay. How do I know it's a decay? 1/3 is less than 1. So it's a decay. I also know that when x equals to 0, I know y equals to 1. Well, let's go ahead and add x equals to 1. See what happens at x is 1. 1/3 to the 1 is 1/3. So I can plot those 2 points and say, I have 0, 1. Then I have 1 comma 1/3. Well, that's not very exciting. 1 comma 1/3 is about here. Wow, look at that. As I go to the right, it must be going down. Well, of course, it's a decay because that's 1/3. So we know that the function is going to go down to the right and approach the asymptote of y is 0. And as I go to the left, it's going to go. Now, if you want to put a negative x just to see what happens, when x is a negative 1, 1/3 to the negative 1 really means 3. You can use your calculator if you want. So as I go to negative 1, 1, 2, 3, it's going to go up there. So you can get a couple more points there. There's my decay. See how it falls to the right? All right, let's see. It is a decay. Its domain. I got a little secret for you. All exponential functions have domain all real numbers. So if you want to do all real numbers, that's the same thing. The range, though, is not all real numbers. The range starts at the horizontal asymptote, which is 0, and then goes up forever. The y-intercept, since I didn't shift it left or right or up or down, 0, 1 is its y-intercept. And y equals to 0 still is the horizontal asymptote. Increases? Nope, none. Decreases? Yes. Negative infinity to infinity. As x approaches infinity, y approaches 0. As x approaches infinity to the right forever, y approaches 0. As x approaches negative infinity to the left, y approaches infinity. All right, there's your first set. Let's move on. Got a couple more here. Not very exciting. It's not exciting at all. 2/5 is still less than 1. Therefore, it's still a decay. When x is 0, 2/5 to the 0 is still 1. So 0, 1 is still, again, an ordered pair. Since it's a decay, we know that this function is going to go down to the right. As it goes to the right, we know it's going to go up. Feel free to try another x. X is 1. 2/5 to the 1 is 2/5. So I know when right here it's 2/5, it's going to be down here. And if you were to go and put x as a negative 1 and find out what happens here, you would find out that it's 2.5. So it actually is steeper than what I have here. Should have been 1, 2.5. Should be more up here. So you can adjust it. Where did I get that point from? I said let x equals to a negative 1. 2/5 to the negative 1 really means 5 over 2, which is 2.5. All right. Boring answers. These are all the same answers we just had the last couple of problems. It's a decay. Its domain is still all real numbers. Its range is 0 to infinity. Its y-intercept is 0, 1. Its asymptote is y is 0. It's not increasing, but it is decreasing from negative infinity to infinity. As x goes to infinity, f of x goes to 0. As x goes to negative infinity, y goes to infinity. I hope this one's a little more exciting because I'm getting kind of bored. All right, I wrote over my problems, so... All right, it's going to be a very, very, very steep growth. How do I know? 4 is greater than 1. And it's a big number. So we know there's going to be a vertical stretch. So it's growth. When x is 0, 4 to the 0 is 1. When x is 1, 4 to the 1 is 4. So why don't I plot those 2 points right now? 0, 1. And then 4, 1 comma 4. Very steep, like I said. And since it's a growth, we know that to the left, it goes down to the asymptote. To the right, it's going to go up like that. I almost missed it, but it's close enough. It's a growth. Domain is negative infinity to infinity. Range is 0 to infinity. 0, 1 is the y-intercept. and y equal to 0 is your horizontal asymptote. It increases all the time from left to right. So it increases from negative infinity to infinity, and it never decreases. As x approaches infinity, it means to the right forever, f of x approaches to infinity. As x approaches to the left forever, f of x approaches 0. All right, let's move on. Oops, didn't mean to do that. E. You've seen the number E before. E is an irrational number. Also, if you want to get really fancy, it's transcendental. Transcendental. It's one of those weird numbers that we notify it as an E. Approximate value will be approximately 2.718, but it goes on forever. That's why it's irrational. It goes on and on and on and on. Exponential functions with base E are called natural base. And we use them a lot in real-world applications. We use base E a lot in science, in physics, and in chemistry. Let me write f of x equals e to the x. The base is e, so f of x is approximately 2.718 to the x. And since 2.718 is greater than 1, it is a growth. And just like I did on the other problems, since 2.718 to the 0 power is 1, then I know at 0, it still goes there. 0, 1 is still going to be the Y-intercept. Now, if I want to know what happens when x is 1, just talking another point, well, e to the 1 is just e, so that's 2.7. So if I go to 1, it's about here. So there's my growth. There's my beautiful growth. And since it did not shift up or down, it's still going to go just like the other exponential growth problems. Growth. All real numbers. Range. Y is greater than 0. 0, 1 is my y-intercept. And the horizontal asymptote still is y equals to 0. And it increases everywhere from negative infinity to infinity. And this one never decreases. As x approaches infinity to the right forever, f of x approaches infinity goes up forever. As x approaches negative infinity, f of x, that's to the left forever, approaches 0. All right, there's your first part of exponential growth. Moving on. We're going to now, we're going to shift. I'm going to call this topic shifting. Shifting exponential functions. That means moving up, moving down, moving right, moving left. The good news is all the rules you've learned about shifting functions always apply. When you add a number to the x, you're always shifting it to the opposite direction. We add, we go left. If we subtract, we go right. If the function has a number outside of it plus a number, we're shifting up. If we're taking away a number at the end, we're shifting it down. Those are the common ones. If you take a function and you multiply a negative in front, it goes upside down. Remember, like if we looked at y equals x squared versus y equals negative x squared, it flips upside down across the x-axis. If only the x is getting the negative, it flips over the y-axis. What else can we talk about? Here's my a that we didn't have earlier in the other lesson that they definitely wrote a all the time. If a is a number that the absolute value of it is greater or less than 1, we call that a vertical compression. I called it a shrink, like it's a vertical shrink. It pushes it down, it compresses it. We've had that before when the number was less than 1, like y equals 2/3 x squared. Even if it was y equals negative 2/3 x squared, it becomes fat and wide. And if the number is going to be greater than 1, like this, it doesn't matter that it was negative, it just didn't matter. I just meant it flipped it upside down. It's going to be a vertical stretch. So we'll talk about those. The harder one is when we talk about stretching it horizontally. You're looking at, well, what number is being multiplied by the x inside the function. If that number is less than 1, whether it's negative or positive, you take the absolute value, then we call that a horizontal stretch. And if that number is greater than 1, that's a compression, a horizontal compression. It means it gets skinnier. Those are hard ones to do. All right, directions for this one is just talk about, identify what the parent function is, and describe the transformations. So as I look at this one here, okay, b is a 2. Since b is a 2, this is called an exponential growth. Next thing I can see is, since I'm taking away 3 from the whole picture, this causes it to shift down 3 units. The x is being added 1. Since we're adding 1 to x, that means we're shifting, wait for it, left 1 unit. So if I was to just think about it, here is y equals 2 to the x. Here it is, generically. And this is what's happening. This function here that went through 0, 1 will go down 3. 1, 2, 3. And that same point that I put down here, 3 down, has to shift left 1. So it actually goes left 1. So the real graph of that function is going to look like this. I got to make sure what else goes down. It's going to do something like that. Because it has to shift left and it has to shift down. So that would be that function here, at least roughly. Okay, he didn't ask us to graph, so I won't graph the rest. This is less than 1, so it's a decay. What happens to this decay? It shifts up 1. And it shifts right 5. And what does this do? Flips over x axis. Okay, there's a lot to chew with this page. All right. Okay, I see he's throwing a lot of stuff at us on this one. This causes it to shift down 7 units. This x is taking away 2, so it means it shifts right 2 units. This means it's going to be a growth. The negative means flip over the x-axis. And last but not least, the 3 means it's going to be a vertical stretch. A vertical stretch. That's a mouthful. What we should do is graph this function, just 4 to the x, compare it. Y equals 4 to the x. And then graph every one of these things one at a time to see what it does. That would be a good activity for you to do, is go ahead and do the next one, do y2 4 to the x minus 7, and see if it does go down 7. And then do y3 4 to the x minus 2 minus a 7, and see if it does go to the right. Then go ahead and do y4 negative 4 to the x minus 2 minus 7. See if it flips over the x-axis. And then do y5, put a negative 3 times the 4 to the x minus 2 minus 7, and see what happens if we do get a stretch. Maybe I'll do that at the end, just to put all that on there and see all those steps working. That'd be a good one to do, actually. All right, what transformations are going here? Okay, E is an irrational number bigger than 1, so it's going to be a growth. Plus 5 means shift up 5 units. There's nothing being added to the x, so it does not shift left or right. But there is a minus in front of it. That means what happens is it flips over the y-axis. It flips this negative x, causes it to flip over the y-axis. Then there's a number in front of E. It's 4/3, and 4/3 is bigger than 1, so it's going to be a vertical stretch. Boy, they're getting really complicated here. 5. Okay. Shift down 9 units. Look what's happening here. Now, there's a trick here. He's trying to trick you. You think that it's a minus 4, which would normally mean shift to the right 4. But there's a negative out front of this parenthesis, so it's really a negative x plus 4. I think it shifts 4 left. I think this negative here flip over the y. Growth, vertical stretch. The only way you can get this in your head is if you actually graph them with your calculator and prove that I'm right or wrong. Decay, flip over x-axis. Oof. There is a 4 in front of the x. Horizontal. Oh, I want to call it a horizontal. Let's take a cheat sheet up here. Let's see. Right here. The number. Is that where we're looking at? A number in front of the x. If it was greater than 1. Horizontal compression. I wanted to say a stretch, so I was going to be wrong because it's greater than 1. So I'm glad I looked up there. Horizontal compression, because that number is bigger than what the absolute value of 4 is 4, which is greater than 1. That one doesn't come up very often. We just don't see it very often. But this author wants us to jump through all the hoops. Okay. E makes it a growth. Plus 4 means shift up 4. This minus means flip over the x-axis. That number multiplied in front of the x, since 1/2 or the absolute 1/2 is less than 1, it's a horizontal stretch. Yikes. I didn't say if it was a growth or not. Yeah, I did. Number 8. 3/4 is less than 1, so it's a decay. This minus means flip over the x-axis. This minus 1 means shift down 1. And now I'm looking at this problem, and I think I made a mistake above because I don't want to distribute the 3. I think I distributed negative before. This thing, the 3 is pulled out for a reason. It's going to shift left 2. Oh boy. Okay, so anything else I missed? Oh, the 3 itself means a horizontal compression because it's bigger than 1. So let me go find that problem where I think I gave you the wrong answer. Let's see. Where was it at? Where were you, you dirty dog? Let's see. Oh, there it is. I'm not going to distribute that after all. So ignore this. I'm going to not shift it to the... Did I even write it? Yeah, right here I wrote... I didn't write it down somewhere. If I keep the negative outside of it, like it was, then this makes it go to the right 4. Shifts right 4 units. It's still going to have a flip over the y-axis because there's that negative in front of the x. All right, there's what's he. That's wrong, so take that off. Okay. And every one of these, what I didn't do it said identify the parent function. So I should have done that for step A, should have been like the parent function of this was 2 to the x. The parent function for this is y is 1/2 to the x. The parent function for number 3 was y is 4 to the x. And number 4, answer A would be y equals to e to the x is your parent. Everything else added to it was shifting it, changing it, transforming it. A for number 5 was y is 2 to the x. I think you got the point. That's the next page. All right, graph each function. All right, so, and identify the characteristics. What I like to do is do a rough graph of the parent. So my parent will be y is 3 to the x. So let me just do that in red. 3 to the x has to be a growth going through 0, 1. So there it is. Close enough. It's just a rough graph, okay? I know it could be steeper than that. But what's happening to the parent? Let's take a look right here. I've got down 4. I've got right 1. That's it. Down 4, right 1. So what I'm going to do is I'm going to take this dot here. 1, 2, 3, 4, right 1. I'm going to draw it right here. And you know what else changes? This horizontal asymptote on the parent, which is 1 underneath the dot, would stay the same. 1 underneath the dot. See that? So now I know my graph looks like this. Goes towards this. Boom. It goes up this way. Very simple. So the answer is not the red. If you want to go back and erase that, you can. And say, I was just cheating here. That's not true. But I personally would not go ahead and erase that. That's just what I use to help graph the new function. So its domain, again, is all real numbers. That doesn't change. Its range now, be careful. It's not greater than 0. It's y is greater than, interesting point. If the asymptote went down 4, because it was a -4 in front, everything was a -4, so that's a -4. Y is greater than a -4. Y-intercept used to be 0, 1, but not anymore. Now it's 1, -3. 1, -3. Its horizontal asymptote used to be y is 0, but now it's y equals to a -4. It's increasing. That doesn't change. -infinity to infinity. Decreasing never. As x goes to the right forever, f of x does go up forever. As x goes to the left forever, f of x approaches the horizontal asymptote, -4. Not so bad, was it? All right. I'll do one more here with you. The parent is y equals 1/2 x. It's a decay. So let me do it with a light color. 0, 1 used to be the y. That's too thick. I'll just use the regular color. 0, 1. But this caused it to shift up 2. It does not shift left or right, but it does flip over the x-axis. Flip over x-axis. That's all that happens. So that dot, well, remember, and it was a decay. It's a decay. So it had a horizontal asymptote here. But this dot, now I'm going to do it in red. This flips over here. And this decay that looked like this has to flip over. So it's going to do this. Here's my picture. It may be, it something like that. Because it had to flip over. Was a decay that flipped over the horizontal line of y is 0. So there you go. Domain, all real numbers. Range, y is less than 0. Because it goes down now, it doesn't go up. Y-intercept used to be 0, 1, now it's 0, negative 1. Asymptote still is y is 0. Increases, haha. It does increase from negative infinity to infinity. Decreases, none. As x goes to the right forever, f of x goes to 0. It still goes to 0. As it climbs up, it still goes to 0. As x goes to the left, f of x goes to negative infinity. It's a little different. Oh, one more. Let's see. Okay, it's a decay because the parent function is y equals 1/4 to the x, so it's a decay. But the plus 5 means left 5, and the 3 means it's a vertical stretch. So my original parent had a y-intercept there, and it was a decay, so it was going to do this. There's my original parent function, something like that. So now the new function shifts left 5, so that dot here goes 1, 2, 3, 4, 5. Has to go here. So this still is going to go towards the same asymptote. Okay. But since it's a vertical stretch of 3, this dot goes 1, 2, 3. It's actually going to be up here. So even though it goes through here, it's got to cut through. There's your stretch. Gets a little complicated. Be a bit easier to erase everything I don't like, but that 0, 1 became a negative 5, 4. Negative 5, 4. That's the hard part. Negative 5, 4. That's where that dot became. Where is the y-intercept? The y-intercept is going to be a little harder. Y-intercept happens when x is 0. So 3 times 1/4 to the 0 plus 5 is 1/4 to the 5th. So that would take a calculator to know exactly how small it is. But it's small. 1/4 times 1/4 times 1/4 times 1/4. 4, 16, 30, 164. Very small. It's almost touching the x-axis. All right, let's see what's next. Well, there's still more problems. I think I've done enough for you. Play around. You only got 3 others I haven't tried, and then there's that homework. This is your homework. All right, I'm gonna let you loose. Have fun. Okay, pre-calculus students, for your second lesson after Christmas break, we just got done doing graphing exponential functions. And I did not use a calculator a single time for the ones I showed you because we just need to have the idea of where it looks, a couple good points, and what does it look like as I approach infinity, what does it look like as I approach negative infinity, are pretty much the important features that I need you to understand. We're going to go into now graphing logs. So the generic version of a log was log base b of x equals to a. And so I'm looking over here at the first two examples. He has a log and he has a exponential. If you recall, they're very much related. He starts out letting us know that not only are they related, they're inverse of each other. In a sense, they're mathematical opposites. So if I do a very generic graph of log of x, it's going to look like this. Asymptotic vertically, going up, 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 and going up and over that way. And I can tell you right now that that ordered pair is 1, 0. And you might be thinking, why was I so smart? How do I know that? Well, because this is log base 10. And it is the inverse of 10 to the x, which is exponential growth. Exponential growth meant as it goes to the left forever and ever, it's asymptotic on the horizontal. Then as it cuts through, it goes through the point, wait for it, 0, 1, and then the function continues to climb. Now, those two pictures, if you superimpose them on one graph, you have the exponential growth, then you have the logarithmic growth. Logarithmic growth did this. And if I extend this exponential curve a little more, you can see that there's some symmetry here. And of course, I did a free graph, so you can't really see it. But if I was to make an invisible line as y equals to x, it basically cut that picture in half. I want you to realize that this kept going this way. This keeps going this way. You see how that red dotted line is the middle of it? And then it cut through here. And then you've got on this side of the dotted line going straight down. And on this side of the dotted line, it goes straight across. Asymptotic horizontally, asymptotic vertically. Inverse of each other. That's what an inverse does. If you graph a function and its inverse, it always graphs as a nice pretty picture cut by y equals x if you wanted to graph that line. Okay. What did he write? To graph a logarithmic, you can use the inverse exponential function, then invert the values. He means switch the values in the table. In other words, I had 1, 0, then I know 0, 1 had to be on the graph. that might be what his method will be doing. So I guess I'll try that way. If we're graphing log base 3 of x, the exponential function was base 3. In this case, that's his y value. So that would have been the exponent equals to x. So if you could say to yourself, well, let's see, if I was doing 3 to the y equals x, and that's just an exponential function, because 3 is the base, and you make a table of x's and y's. I don't think I'm going to do it this way very often, just do it one time. If y was a 0, then the x is 3 to the 0 is 1. So I know 1, 0 has to be a point. Well, I showed you that a minute ago. That would be definitely a point. Let's do, what if y was 2? 3 to the 2 is 9. So now I gotta go 9, 2. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2. Oh, yeah, look at what I see. This graph that looks like that. What do you think's happening to the left? Let's see, let's try a number that, what if I put a 1? I put a 1 there, if y is a 1. 3 to the 1 is 3. 3, 1. That doesn't really help. 1, 2, 3, y1. Yeah, that's on the line. So I would have to have something like a fraction. Like, what if I use a half? 3 to the half means the square root of 3. Well, isn't that between 1 and 2? 1.7, approximately 1.7. So that meant, actually, is that right? 3, square root of 3. X is 1. Yeah, x is 1.7. So it makes it a little more complicated. I'm just going to go down and just finish graphing the function. Oh, I did the right one, through square root of 3. Basically, what I said to you is that your log function will be asymptotic to the y-axis. It's going to go up and cross the x-axis, then it's going to go increase forever and ever, up and over, up and over, up and over. So the domain of a typical, this log, since there was no shifting left and right, what do I mean? I didn't go plus a number. I didn't add anything to the x. I didn't add or subtract to the x. I didn't put any negatives anywhere. There's your parent function. The domain cannot be 0, but it can be all the other x's forever. The range can go down forever, and up forever. So negative infinity to infinity. The x-intercept was at 1, 0. If you recall, on the other lesson, we were asking for the y-intercept. We don't have a y-intercept in a log unless we shift it. In this basic log, we do not have a y-intercept. There's a vertical asymptote at y equals to 0. It's increasing from 0 to infinity. This is never decreasing. As x approaches infinity, that means to the right forever, f of x is approaching infinity. As x approaches to the left forever, f of x is approaching, it's always going to be approaching 0. It's never going to approach past that 0. Okay, there's one that I'd want you to be able to do by hand without a calculator. But feel free to try it with a calculator and see if you can make your answers fit. Now this one, because the base is a half, I hope you remember that this meant in exponential was the base is a half to the y equals to x. That was an exponential decay. So what you're going to find out is that the exponential decay is going to be the opposite direction than the exponential growth was. In other words, this is going down forever. The exponential decay will give us a log that goes up forever. Let's see if we can make it work. Let's make a table again, which is not my favorite way of playing around. But let me plug in some x's, some y's I mean. Let me plug in y is 0. 1/2 to the 0 is 1. So there again, I have 1, 0. There's your x-intercept. May as well put that there. 0, 1. Then let me plug in a y value of 2. 1/2 squared is 1/4. Oh, doesn't go up very high. I mean, it doesn't, the x is 1/4. 1/4 is about, you zoom in here, and I put in a 2 for the y, so it's up here. Oh, do you see what's happening? Do you believe me now? So I don't really have to do any more. I can do one more. I can try to see what happens. What if y is a 10? Well, unfortunately, it's going to put it back in the same place. It's going to put it 1/2 to the 10th is 1 over 2 to the 10th. 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024, 1 over 1024. It's very small. Very small. It's going to be way up here. Up the tip. So that's what's happening here. It just keeps getting closer and closer to the y-axis going up that way. So here's my rough graph. You want to go to a calculator and get you another point that might work nice and pretty? Feel free. Asymptotic to the y-axis. That's going to come out. It's going to continue out something like this. It's just the flip of this one here, if you think about it. So the domain, again, starts at 0, goes to infinity. The range is going to be all real numbers. Does it asymptote? Yes. Y equals to 0 is still the asymptote. Increasing? No. It doesn't have any decrease. It's not increasing. It's decreasing. From left to right, it's going down to the left. So it's going to be from 0 to infinity. And behavior? As x approaches infinity, f of x approaches negative infinity, because it goes down. As x approaches negative infinity, f of x, well, it's always going to be approaching 0 again. It can never go to, actually, it's possible that the solution doesn't even, it is possible the solution says it doesn't have, and this doesn't really exist, because it can't go to, that might even apply for this one up here. But I don't know. I'll have to look at it. There's two basic graphs that I would want you to do without a calculator. Oh my goodness. Not the y was 0, it was x is 0. X is 0. I should change these. It wasn't going to 0. I'm sorry. X went to 0. X is going to 0, but y is going to negative infinity if I was to keep that answer. And this was going to positive infinity if I was to keep those answers. Unless you wanted just to get more perfect. Now, what happens as we do natural log? It's no different. It's absolutely no different than the log. Because remember what this means. This means base is e to the y equals to x. So again, if I make my table and I say, well, let my y equals to 0, I get 1 again. So who am I kidding? And e is a number greater than 1, so it's going to be the same picture that I did a minute ago. It's just going to be a different values that would be in the table. But I'm okay with you doing this and saying there's your natural log graph. I don't need perfection. Just need you to understand the concept. From 0 to infinity, all real numbers is your range. 1, 0 is my x-intercept. Y equals to 0 is still my... Oh, what am I doing on every one of those? Yeah, y equals... It was x equals to 0. Did anybody catch that on the other two problems? I feel ridiculous. That's what happens when you're working at 5 in the morning. Increasing. It's always increasing. It's always increasing. From 0 to... Oh, what did I do that for? 0 to infinity. Never decreasing. As x approaches infinity, f of x approaches infinity. As x approaches to the left, negative infinity. Well, again, it never can approach negative infinity. So even though I'm saying f of x only approaches 0, it is possible that the author doesn't even address that. It just says that you can't, it doesn't approach negative infinity. It can't approach negative infinity. So there is a good shot that he doesn't address that, because it really doesn't go to negative infinity. Do another graph with a transformation. Now, the only thing difference is there's a plus 1. And so this logarithmic decay, why do I call it a logarithmic decay? Because it came from a decay exponential. It was a decaying exponential, which meant that the exponential would have been doing this. Okay? So what I'm going to do is actually flip this over. That was a decay. And we know what a decay did. A decay ended up doing on the exponential look like this. Went down like that is what it did. Almost looks the same, except it's not in the same graph. If you graph them separately, if you were to graph y equals x to the 1/3, you would see it differently than log of 1/3 of x. If you were to graph those two together, you would see symmetry on the y equals to x. But anyway, it's going to be shifted one up. So all that changes is that we pretend that this axis here, I just draw it up here. And I say, well, there's my new axis that I care about. So the only point that I'm going to address that changes is the 1, 0 actually became a 2, 0. Because in the normal, it'd have been 1, 0. But since everything gets shifted up 1, it's up here. That's my... So now if he asks me for my x-intercept, it's going to be harder. And he does ask for it. And it is harder to do. We'll try it in a second. But the y-axis still is my asymptote. So I'm going to draw towards it. And now it's going to come down this way. So everything looks the same, except you can tell that the x-intercept point moved up. Every point moved up 1. So the domain is still the same. From 0 to infinity. The range is still all real numbers. Now the x-intercept is going to be harder to find. And I don't know how important it is to find it, but we will try to use some algebra here. Okay, so if I want to find out what happens when y is 0, that's this bad boy here. If y is 0, log 1/3, base 1/3 of x plus 1. Okay, let me try to solve this for x. That's what I want to find out. I want to know what x is when the y is 0. I want to know what happens when the y is 0. What is the x? That's what I'm looking for. So here goes. Subtract 1 from both sides. Log of 1/3 x. Log base 1/3 of x. To get rid of the log base 1/3, I will exponentiate both sides 1/3 to the power. 1/3 to this side. In other words, both sides are being raised up. So this 1/3 to the log of 1/3 basically cancels out, leaving x equals to 1/3 to the -1, which means if you think about it, the 1 gets a -1, the 3 gets a -1. It causes them both to flip positions. So x is equal to 3. Because if 1 gets a -1 and the 3 gets a -1, what happens is the top has to go to the bottom has to go to the top, leaving a 3 to the 1 over a 1 to the 1. 3. So there it is. There's your at 3, 0. Which, see, how accurate am I? 1, 2, 3. Not very accurate. So if I wanted to, and if I would have done that first, it's not a bad idea, I guess, if you want a better picture, but I want to erase. Oh, X, boom. There it goes. Okay. I want to fix this up just a tiny bit. Then I can easily just do from there to curve in there. There you go. Looks okay. Asymptote is still going to be the y-axis, not y is 0. Y-axis. X is 0. Increasing? Never. It's decreasing from 0 to infinity. As x approaches to the right forever, f of x is approaching negative infinity. As x approaches to the left forever, f of x only is approaching 0. F of x... Wait a minute, was I wrong on the other one? Hold on. As x... We're talking about y, I'm sorry. F of x approaches infinity. What did I write up here? As x... I'm so wrong on all of those. I am going to fix them all right now, right in front of you. I'm not talking about... Well, I'm talking about what y approaches. Well, no, it's the same thing. It's the same thing. Does x ever approach negative infinity? No. I guess it's the same kind of idea. As x approaches to the left, f of x is going up. But again, I don't think he's going to let me do that because I can never really... I'm truly not going there. Let's do one more. Now, this transformation is that I am subtracting 2 from the x, which means right 2. Ooh, and there's a negative in front, meaning it flips over the x-axis. So I'm going to do a cheater method with you right now. I'm going to draw the parent, y equals 2 log base 2 of x. That looks like this. It's just a log, no shifting at all. Goes through the 0, 1, or I'm sorry, 1 comma 0, and it goes up forever, and it comes down forever, asymptotic to the x-axis. This picture has to flip upside down, and it has to shift to the right too. So what I'm going to do is I'm going to take this dot, 1, 2, I move it here. I'm going to take this asymptote that's right next to it, and I'm going to move it to 1, 2. So here's my asymptote now. Also, what else can I say? I went to the right 2. I need to flip over the y-axis. So what I'm going to do is take this picture here, and I'm going to draw it one time. I'm going to draw this here. Here it goes. Here is the shifted to the right 2. But this picture has to flip upside down. So what will the new picture look like if that flips upside down? I'm using my imagination. Now this thing going down is going to be coming from up here. Oops, not drawing. Yeah, there it goes. I quit drawing again. Come here, and it's going to have to go like this. I think that's the black flipped upside down. The blue was the original parent. I shifted it with the black 2 to the right, and now I'm flipping it upside down, reversing the whole picture. Does that make sense? So check it with your calculator, And I'm going to erase the stuff that doesn't really belong to that picture anymore. None of this really is part of the picture anymore. None of this is part of the picture. Check it with your calculator. We will still have to answer the basic questions, the domain. This time, the vertical asymptote changed from 0 to 2 because it shifted right, so it's 2 to infinity. The range is still all real numbers. The X-intercept, did I actually calculate that? I haven't, and it shifted. So let me go ahead and do that work here. The original function is y equals to negative log base 2 of x minus 2. And so we want the y to be 0. So 0 equals to negative log base 2 of x minus 2. And get rid of the negative. Both sides still gives you 0 equals log base 2 of x minus 2. Exponentiate both sides to get rid of the log base 2. This goes away. This becomes 1. 1 equals x minus 2. Add 2 to both sides. 3 equals to x. So it's 3 comma 0. It's a good skill to do. Asymptote now is the x equals to 2 because it moved over. Increasing is never. Decreasing is from 2 to infinity. It's constantly decreasing. And behavior, the only end behavior I'm going to say I have is as x approaches infinity, f of x approaches negative infinity. I won't even do the other one because it's not approaching negative infinity. Okay, I'm going to do one more because it uses 2 transformations also. And then I'm going to be done. I'll assign you the other problems. The transformations in this one is a shifting down of 2 and a shifting left of 5. Down 2, left 5. If you want to make your life easy, draw your parent first. Log base 4 of x. It's very simple. Log base 4 of x means it had to go through 0, 1, and it's just a normal log curve, goes up, 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 over, over, over like this. Something like that. Okay? But there's 2 shifts. There's a shift down and there's a shift left. So think about it. This point right here has to go down how many? 2 and left 5. So watch this. Down 2, left 5. 1, 2, 3, 4, 5. It has to be over there. And the asymptote had to go left 5. 1, 2, 3, 4, 5. So here is your new asymptote. So that same picture, here goes. It's going to look the same, except it's going to go through this point down here now, and now it's going to go up. There it is. This is a good representation of the new graph. You could make a table. You could play with points. The only point that he's asking me for is my x-intercept right here. So I'll do the algebra. Original problem. y equals to log base 4 of x plus 5 minus 2. Make that the 0, like we did before. Log base 4 of x plus 5 minus 2. Add 2 to both sides. 2 equals to log base 4 of x plus 5. Exponentiate both sides. 4 to that power, 4 to that power. This cancels out. 4 times 4 is 16 equals to x plus 5. X must be 11. So the ordered pair would be 11, comma, let's see, is it going to be 11, comma 0? Doesn't look like it. It should be negative. Let me look. Oh, wait. 2, 4, 16. Hello, I'm ready. I'm done.
Huh?
I'm done.
Okay, I cook breakfast in the kitchen.
Oh, okay. Let me get up. Let me,
I put foggy outside.
is it really? My fingers are numb right now.